Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be doing binary search. So, the contents of this lecture will be how to search an element, and then we will go into details of binary search. So, the problem is very simple. We have been given S, which is a set of objects, and someone has asked us, is a new item X, is it in S or not? This is the kind of problem that we encounter in our everyday life, also in lots of computer programs, and also as subtasks of many more complicated computer programs. So, this is one of the most important in subject of algorithms. So, for example, say you have a set of clothes in your cupboard, and you want to check whether a particular red colored cloth is in the cupboard, something we do every day, and we would like to know how to check it. You have been given a list of names of people who have got first division in an exam, and we want to check if your name is in the list. Again, something that we do it regularly when the list is put up somewhere, and of course, the computer has to do it regularly when people make queries to the computer. Is this number or roll number or name is in the list of people who have got the first division or something. The third thing is, we have a set of words in a dictionary. You can think of this dictionary as either a book dictionary that we have at home, or the dictionary that is stored in the computer as a E format or something, and we want to find whether location of a particular word. Here we do not want to check whether a particular word exists or not, but actually the location of that word in the dictionary. How do we do it? So, these are some obvious examples, and what is the mathematical setup of this? So, we have a set S, which we say contains n elements, which is S1, S2, S3 up to Sn, and we have been given a new item X, and we want to check if X is in this set S, right. So, for example, I have this set S, which is a set of integers. I will be using integers for the rest of my lecture just as some object. You can replace these integers as numbers on charts, names, anything. Say I have this set, which is a set of integers, which is 2, 4, 1, 8, 10, 5 and 3, and I want to search or check if 7 is in this set or not. Now, everybody must be thinking this is a very stupid question to ask. All of us can do it, and that is, you are right, all of us can do it, and the usual thing that we do is an exhaustive search, which is we first go to the number 2 and see, we first go to the first element, which is in this case number 2, and see is 2 is equal to x. If not, we will throw it or mark it red or something. Then we go to the next element, which is 4 in this case, and we ask, is 4 equal to 7? No. Go to the next element, is 1 equal to 7? No. and similarly we keep on going for all of them one by one and check if 7 is one of these elements. At the end, if we do not find 7 and we have exhausted the whole set, we say 7 is not there. Of course, in the middle if we had encountered 7, then we would have output that yes, it is there and this is the place where it belonged. So, let us see the pseudo code of this algorithm. So, we have been given this set S and X, these are the two inputs that we have been given, this set S and X, and we want to check if X is in the set S. So, what we do? We go from left to right one by one, exhaustively searching the whole set S, and for I equals to 1 to n, if X is this ith element, that means I find out X in this set. In that case, I output I, which is the position of X in S. Else, what do? I do not find X yet, I just increment the index. So, I equals to I plus 1. Now, I continue this particular for loop till for n steps, that means for all the elements in this set S. After this for loop, if I had not output anything till now, in that case we come here and note that in the last round when I equals to n, I have not found x equal to S I, I have not found it. So, I have increased it. So, I have become n plus 1. At the end, if I check that if I is greater than n, that means in n plus 1, then I will output not there, because I have exhausted the whole set and I have not found the thing that I was looking for. So, as with all algorithms, we have to first check the correctness and termination. In this case, the correctness and termination is much easier. Say if x is in S and if x is say the ith element, then when the ith round is going on, of course, this if condition will be satisfied and hence the output will be made. Okay. So, thus if x is in this set, then the algorithm will output something and terminate. But if x is not in this set, then after this whole for loop, we will be left with I equals to n plus 1, because in the last round I will have I equals to n and will go through n plus 1, and then in this if condition will be satisfied and we will be output not there. Thus, in either case we will terminate and we will output the right answer. So, the correctness and termination is not something very hard to check in this algorithm. The time and space complexity, this is again not that hard to check. The for loop of course goes for n rounds, so it takes some n steps. So, the number of comparisons, so in this case we just say count the number of comparisons more than the number of steps, and how many comparisons are there? The comparisons is done only at two places, here and actually that is it, not even two places, one place. This is not a comparison, because this is just an indexing in some sense. Thus, the number of comparisons will be n. Space complexity, how much space we need? It is constant, because we do not have anything to store as such, right. All we are storing is I, which is like it is a register keeping. So, the space complexity is constant. Now, the obvious question, can we do better than this? And sadly the answer is no. I mean, we have seen it almost in our day to day life. If in a cupboard we have a lot of clothes and we are looking for a particular cloth, we can, all we can do its best is go through all the clothes one by one. Or in our desk, if you have a lot of papers or files and after looking for a particular file, the only thing that one can do in the worst case is go through all the files or all the papers one by one. So, not much can be done with this. But what happens if this set is slightly bit more structured? Say the files in my desks are ordered in a particular way, or the clothes in my cupboard are neatly arranged and folded and placed in a particular shelf depending on the color or something like that. In that case, can we do better? So, here is the most important structure that a set can have, particularly when we talk about things like integers or names or some things on which a ordering occurs naturally. This is a place where this S being a set of integers is very important, because integers have a particular ordering. 2 is less than 4, 4 is greater than 1, this is strict ordering. In the case of clause, for example, there is no such ordering. Canonical ordering does not exist. In the case of words in a dictionary, there is an ordering, and we do use it, correct. The words are stored in the dictionary in a particular order, and we look for it. We go first to, say we are looking for this word cow, we will first go to C, and then from C we will go to O. So, we have ordering, and which helps us to guide. Searching in a sorted list is very important tasks. In a computer programs, we face it regularly. For example, say in this example, the same example we did earlier. So, S was this set 2, 4, 1, 8, 10, 5, 3, and we want to check if 7 is in set S. Now, we cannot do anything better if the set has been given to us like this. But if the set is ordered, and say in the ascending order, in this case say for S is, so I have just arranged this number so that it is ordered now 1, 2, 3, 4, 5, 8 and 10. The question remains same. All that I have done now is that added a new structure to this set, and the set has become sorted. And question is that can we find 7 in this sorted list? So, let us see how do I sort in this sorted list. So, to start with, what we do is that we first see that we have to find it out in this section. I will put this square bracket in the beginning and the circle bracket at the end. So, what we do is that instead of going and searching one by one from left to right, we instead go to somewhere in the middle. So, there is 1, 2, 3, 4, 5, 6, 7 elements. 7 by 2 is 3.5. So, we go to the fourth element, which is 1, 2, 3, 4, and we check this fourth element, and we ask is 7 greater than this number or less than this number. Now, in this case 7 is greater than this number, since it is sorted this list. So, if 7 at all occurs, it must occur in this left of this number, right. So, we first go to 4, we get the answer that 7 is greater than this number, and now we know that it cannot be in the left of this number, that in some sense we can strike off everything before, or rather we can push this square bracket up to 4, because we know that if at all it exists, it is in the 4 and above. Now, we are left with a sub problem, a sub task of finding 7 in this smaller list between. So, we are now have, so initially this one was the index 1 and this one was index 7, and after this first round we have pushed our lower boundary from 1 to 4. What is the next place to check? Again we can do the same thing as go and search for this set, this list set over here, and check for each 7 being equal to 4, 7 being equal to 5 and so on. Or we can do a slightly more clever job, which is go for the middle element. Now, what is middle element? 4 plus 7 is 11 by 2 is 5.5. So, it is this sixth element in this, in the whole list that we want to go, sixth index. Which was the sixth index? 1, 2, 3, 4, 5, 6. So, we have to go to this sixth element, which is 8, and check if 8 is less than or greater than 7. Now, again we come here and we find that 7 is less than 8. If 7 is less than 8, what do I know? that it cannot be bigger than that. So, we can strike off 10, or in other words we can bring this circular bracket a bit forward. Thus, we are left with checking 7 is there in this smaller place. Okay, we will take a small break right now and come back and finish this algorithm and see more about it. Thanks. Okay, welcome back after the break. So, we were looking at binary search in a sorted list. So, we started with this set S, and the set S was sorted. So, it is 1, 2, 3, 4, 5, 8 and 10, and we wanted to check if 7 is in this set. So, we first had this indexing that we had, which was we started with the square bracket at 1 and the circular bracket at 7, and the first thing to check was whether 7 in this set starting from 1 to 7. This 7 is not this 7, this 7 is the indexing 7, the index of this particular set element, because 1, 2, 3, 4, 5, 6, 7 is 7. Now, what do? We instead of going from left to right or right to left, we first went to the center, which was the half 7 plus 1 by 2, which is 4. We went to the fourth place, checked for 4. We saw that 7, this number 7 is bigger than 4. Thus, if this 7 exists in this set, it must be on the right hand side. So, we can remove 1, 2, 3. In other words, we can move this window up from the first index to the fourth index. Then we came to remaining set between 4 and 7. We looked at the center place. In center place was 4 plus 7 by 2, which is 5.5, or if we go to the near integer higher than that, it is 6th. So, the 6th index was 8. Compared our element 7 with 8, and we found that 7 was less than 8. In other words, it cannot be higher, it cannot be on the right side of 8. So, we striked it off, or in other words moved this curly right edge up, and now we are left with a smaller set starting from 4 and index 6, and this is the set that we are left with searching. So, if 7 exists, it must be in this set, otherwise not. And what is the next one? The next one is, again we go for the center one. 4 plus 6 is 7. We go for 7, which is the center one, and we check is this one in the 7 or not, and if not, what basically we have got is that we have compared with all 3, or in other words what we can do is now is that with this happening, again we say 7, it says that 7 is greater than 5. If 7 is greater than 5, then again we will 7 cannot be anything of on the left hand side of 5. So, we can strike off this element and we can push our boundary to this. Now, we are left with the 2 index 5 and 6. Again we go to the middle, which is this one, it cannot be less than this. So, we push this one up, down. So, we keep on moving till we have cornered one particular element which can be it. And now, if 7 is not equal to 5, okay, then 7 is not there. So, this is basically the algorithm for binary search. So, let us see the pseudocode of it. So, we have been given this set S, which is S1 to Sn and an element x. This set S is ordered, in this case in the ascending order. In other words, if I is between 1 and n, so for any I between 1 and n, Si is less than or equal to Si plus 1. So, this set S is in the sorted increasing order, and we want to check if x is in this set S. And here is this algorithm. This is just the pseudocode of the algorithm I tried to explain in the with example. So, here are these two things, very important things. We initialize two parameters. One is this L, the other is U. So, L in some sense stands for the square bracket that I was doing. which was the lower end, that is why the L, and U for the open bracket that was doing, which was the upper, that is upper end or U. So, we first initialize L to 1 and U to n. So, we started from this side of the set to this side of the set. That is our initialization. Of course, initially this is the whole set in which we have to look for. And then thing is that as long as L is strictly less than U, we are fine, we will keep on doing something. What will we do? We will every time go to the center place, which is L plus U by 2. So, we will go to the center one and we will check if x is this element. So, let the center one be m, m for middle. So, if x is less than S m, the mth element, in that case what we know? We know that x cannot be on the right side. The right side everything, right side of S m is greater than S m, because the set S was an increasingly ordered set. Thus, we can clearly lower our upper limit to m. So, after this round what will happen is that L will still remain as 1 and U will become m. Else what happens? Else means x is strictly greater than S m. In that case, we know that it is strictly greater than S m, thus x cannot be S m, or it cannot be S m minus 1, or cannot be anything on the left side of S m. We can increase the lower boundary from L to m plus 1. So, L becomes assigned to m plus 1, okay. And we keep on doing it. How long? Till L is strictly less than U. So, at some point of time we hope that L will become equal to U, these two boundaries will come together into one particular thing, and then what we do is that we check if x is equal to S u. If it is S u, we output U, else we output not there. This algorithm looks a bit complicated, but it is a very useful and handy algorithm to have. But before that, we have to prove that this algorithm outputs the correct, it first of all terminates and it outputs the correct value, and then we will understand the time complexity of this algorithm. So, let us start with the termination of this algorithm. The termination of the algorithm is that, note that if L ever becomes greater than or equal to U, then it will terminate, right, because it will then go out of the while loop and then it would check this if condition, and whatever it gets, it will either output U or it will output not there. Now, L never goes down, it starts from 1 and can only go up. It is like we are pushing this L up. The L goes from L to L m plus 1, and m plus 1 is the middle of L and U. On the other hand, U, which is the upper boundary, can never go up, it can only go down, and in every step, every while loop, either L goes up by 1 or m goes down by 1. This is something that you have to verify from here, that either L will go up by 1, so m plus 1 will be strictly greater than m, or m will be strictly less than U, either of them will happen. So, every while loop, either the lower boundary is going up by 1 or the upper boundary is going down by 1. If the lower boundary goes up by 1 and the upper boundary goes down by 1, and at some point of time if these two meet, then the algorithm immediately stops. So, how many steps can it go for? At the best it can go for n steps. So, that ended up the termination of the algorithm. And for this correctness of this algorithm, this is a bit easier. If x, so this is a condition here that is always ensured in this whole algorithm. This is an invariant of this algorithm. We call this one as the invariant, which is that if x is equal to some index I, then this I will always be between L and U. If I can ensure this, then what is the good thing is that at the end when L becomes equal to U, I will be equals to U, and thus we will be finding out whether I is equal to SU or not, and hence output the right value in the if condition. When L is equals to U, then either X equal to SU or does not. Now, let us try to understand why this one happens. This is something we have to prove, that this is an invariant in this whole algorithm. To prove that, we have to go through this while loop. Let us start that at some point of time I is between L and U, and say we come to here and S is less than Sm. If S is less than Sm, that means this I is clearly less than M, and now when we push U down to M, I will still be between L and U, because it will be, in this case we will have L which is less than I know that, which is because of this less than or equal to M, and which is because it is the median of L and U is less than or equals to U. So, when U gets assigned to M, L will be less than. Similarly, you can check it for the other case. Now, every loop has exactly one comparison. So, this was giving the correctness of this algorithm. We have to understand the running time of this algorithm, which is right here. So, every loop here makes exactly one comparison, which is X measuring with X with Sm, right. And every round U minus L, this distance between U minus L is halved. This is again something that we need to check from this whole analysis, not hard to check. I leave it as an exercise for you guys to check, prove that U minus L is halved. And since it is halving every time, thus after log n steps, why n? Because initially U was n and L was 1, so U minus L was n minus 1, so it is around log n steps. After log n rounds, the loop will end, because after log n rounds U will become equals to L, and thus the total number of comparisons will be log n plus 1. This proves that we can search this element in log n plus 1 steps. So, as a summary, we had an exhaustive search algorithm which finds an algorithm in the total size of the set number of comparisons. But then we looked at binary search algorithms, where the number of comparisons made was increased from n, which was in this case, to log n plus 1. So, in logarithm number of size of this set, one can check if an element exists in a sorted list or not. So, here are a few questions. I have not done the space complexity of this binary search algorithm. I leave it to you guys to verify how much is it. This algorithm that I presented when the list was sorted in an ascending order, if the list is sorted in a descending order, a slight modification is to make. And the last question, which is a bit more complicated, is if I give you n numbers, say sorted in an ascending order, can one find an element from this list in less than the number of comparisons that a binary search makes? So, with this we conclude this lecture on binary search. In this next lecture, we will see more uses of binary search for advanced algorithms. Thanks.